We saw at the end of the last video how the motion of the ball that was thrown up by a passenger in the train, that event is observed by two different observers in two different ways. For a co-passenger traveling in the train, the ball seemed to go up and down in a vertical direction. It was a one-dimensional motion. Whereas for a person on the ground, it seemed like a parabolic motion. So the frame of reference is very important when talking about observations of events. There are two types of frames of reference that can be distinguished from each other. The first one is called the inertial frame. You can think of an inertial frame as basically a reference frame which is moving at a constant velocity with other frames, a constant velocity. There is another way to think about an inertial frame, and that is the following. An inertial frame is a frame in which Newton's first law of motion is obeyed. You'll recall from first semester that the first law of motion is also known as law of inertia. And basically the idea is, unless a force is acted upon an object, it is not going to accelerate. So an inertial frame is one in which, as long as there's no force acting on an object, it will not accelerate. And I'll give you an example of how that can be violated. So inertial frames are frames that are moving at constant velocity with respect to each other, and frames that in which law of inertia or Newton's first law of motion is obeyed. The second type of frame of reference is the non-inertial frame. In a non-inertial frame, first of all, the law of inertia is not obeyed. And secondly, these are frames which are not moving at constant velocity, but they accelerate with respect to each other. To give an example of a non-inertial frame, consider a car which is making a turn. So in the beginning, the car is going along a straight direction, and then it makes a turn. Now, when the car turns, a passenger in the car sitting next to the driver, let's say that the car turns left, then the passenger seems to be pushed towards the right, towards the door, the passenger door. Now, that does not obey Newton's first law because there is no force acting on the passenger. There's no one pushing the passenger towards the door. However, simply the act of turning causes that to happen. So the reason for that is it's a non-inertial frame, meaning the car, if it makes a turn, even if it turns at a constant speed, if it makes a turn, it is not moving at a constant velocity anymore, it is accelerating. So in accelerating frames, you don't expect Newton's first law to be obeyed, and those are known as non-inertial frames. There are two types of relativities. First of all, the first type is known as special theory of relativity, and this is relativity applicable for inertial frames. So special relativity, which relates to inertial frames. And then you have general relativity, which is applicable in non-inertial frames. In this course, we will confine ourselves to special relativity, and we'll come up with some equations relating to mechanics, relating to kinematics, relating to dynamics, equations of motion, and so forth. And we'll see that the structure of these equations seem very different from what it was in classical mechanics. However, if the object is moving at a slow speed, then the equations of special relativity basically become identical to the equations of classical physics. So the distinction of special relativity is valid only at high speeds. If things are moving at slow speeds, then we might as well just use classical mechanics. We don't need special relativity. Now, the distinction between fast and slow may seem arbitrary, and to some extent it is. However, we say that something is moving at a slow speed if the velocity is less than 0.01 c. So if something is moving at a speed less than or equal to 1% of speed of light, then we consider that to be a slow speed at which we don't need special relativity. We can use classical mechanics. And such speeds are known as non-relativistic speeds. However, if an object is moving at a greater speed, then we do need special relativity, and those speeds are known as relativistic speeds. So this brings us to what are known as postulates. Postulates are basically statements which are taken to be true, and they serve as an assumption or a premise for further reasoning and development. So you don't expect postulates to be proven. They are, in some sense, self-evident. Now, it doesn't mean that they're arbitrary. So you build a theory based on postulates, and if you can prove that those theories are correct, then that suggests that the underlying postulates are correct as well. So there are two fundamental postulates of Einstein's special theory of relativity. The first postulate goes as follows. Laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. One way to think about this statement is that a principle only behaves or can only be accepted as a law of physics if it is obeyed in all inertial frames of reference. So if something it doesn't, then it doesn't qualify as a law of physics. The second postulate basically has to do with light. Now, you'll recall from end of second semester, that Maxwell's equations predicted that, first of all, it predicted the existence of electromagnetic waves, including light, and that light travels at 3 times 10⁸ meters per second. Now, Maxwell did not specify a frame of reference for this speed, and we know how different frames of references can result in different speed measurements. If a car is moving at 60 miles an hour, then for a person on the road, the driver appears to be moving at 60 miles per hour. However, for a passenger in the car, the driver appears to be at rest. So whatever speed you measure depends on the frame of reference. So Maxwell said the speed of light is 3 times 10⁸ meters per second without specifying what frame of reference that is in. So after a lot of thought and different experiments, it was established that speed of light is 3 times 10⁸ meters per second, regardless of what frame of reference is measured from. So light travels at that speed. It doesn't matter what the state of motion of the observer is. So that's the second postulate of special relativity. Speed of light is c. Speed of light is 3 times 10⁸ meters per second, independent of the relative motion of source and observer, independent of what frame of reference it's measured in. So again, the first postulate is that all laws of physics are valid, equally valid, and have the same form in all inertial frames of reference. The second postulate is that the speed of light is a constant, independent of the frame of reference in which it is measured. Now, these two postulates are deceptively simple, but they radically change the face of physics. And we'll see how, if the two postulates are correct, then our classical idea of space and time becomes fundamentally altered. Both space and time become relative. In classical physics, space and time had absolute values. If something measures 2 meters, we assume that it will always measure 2 meters, no matter who's looking at it from what frame of reference. If the interval between two events is 5 seconds, then it didn't matter who was looking at it from what frame of reference, that interval would remain 5 seconds. So that's hardball how things were in classical physics. Space and time were absolute. However, when you get to special relativity, both of these entities, space and time, become relative, meaning the length of objects depend on the observer who's making that measurement, the frame of reference of the observer. Same thing for the flow of time. So that brings us to the idea of simultaneity and time dilation, which we will look at in the next video.